Okay, so 10.3, composite functions. If you haven't already got your notes out, go ahead and do that. But what we're doing here today is composing functions of one another. So you'll see what we mean in a minute, but basically what we're going to be doing, instead of adding, subtracting, multiplying, dividing functions, we're going to be plugging different functions into each other. Okay, so go ahead, if you want to pause the video, you can go ahead and try the warm-up. Given f of x equals 3x squared plus 4, you're going to find three things: f of 1, f of a, f of g of x. So go ahead and give it a shot. Okay, so here we go. Plugging each one of these in, I'm just going to go ahead and replace the x with whatever the notation is instructing me to do. So in the first case, I'm going to plug in a 1. So 3 times 1 squared, 3 plus 4, I get 7. In the next one, it's instructing me to plug in an a in place of the x. So 3 times a squared is just 3a squared, and then plus 4. And the last one looks a little funny, but the notation's the same. It's just asking you to plug in g of x in place of the x. So I'm going to do exactly what I did in the other two examples and simplify if you can. This one doesn't really. I can just take away those brackets and get 3 times g of x squared plus 4. Okay, so that's basically the idea of what we're going to be doing today. What we're going to be doing is composing one function of another. Okay, just as we can plug in a given value. Note that we're still really just plugging in something. That's really all we're doing. Now the notation is a little funny. So that's the notation we used in the last example, f of g of x, where I'm plugging in the g of x. Sometimes it's written like this: f with the little circle with g of x. Now that really means the same thing. So if I saw that notation, I would right away go ahead and write the one that's a little more comfortable. Okay? That little circle is the composition symbol. Really, you just have to recognize it and be able to compose f of g of x. So I would rewrite it, like I said. So we're going to work through a bunch of examples here. In example 1, for this whole question, f of x will be 2x plus 3, and g of x will be x squared minus 1. And then we're going to find each of the following. So the first one, f of g of 3. So in this case, we have a particular value, 3. So what this is saying is find the value of g of 3. Okay, so that's just saying go ahead to g and plug in a 3. So that would be 3 squared minus 1, which is 8. And then evaluate f of g of 3, which is actually the same thing as f of 8. Okay, and that's saying go to the function f and replace the x with an 8. 2 times 8 is 16, plus 3 is 19. So f of g of 3, our answer is 19. Okay, so that's if you have a particular value. Find the inside and then plug that into the outside. Okay, in example B, we don't have a particular value. We have f of g of x. Now, the thing on the inside is the function that I'm going to plug in to the other function. So in this case, what they're asking me to do is go to the function named f and replace the x with g of x, just like we did in our warm-up. Okay, so here we go. The function f of x is 2x plus 3. Now I'm going to replace the x with a g of x. So instead of 2x plus 3, I'll have 2g of x plus 3. Okay. Now I can go a little further because I know what g of x actually is. G of x is the same thing as x squared minus 1. So I can plug that in now for the g of x and then simplify this. So if I keep going and I multiply, I get 2x squared minus 2 plus 3, and then 2x squared plus 1. And there's our final answer. So that is the f of g of x function. It's f with g of x plugged into it. Okay? If you want to go ahead and pause it, the final 4 questions here, C, D, E, and F, you should be able to do. So give it a try. Okay, so looking at example C, this time I have a value again. So I'm going to go ahead and find f of 3. So plugging 3 into the function f, I get 2 times 3 plus 3, which is 6 plus 3, 9. And then I'm going to go to the function g and plug in f of 3, which is 9. So So when I do that, I get 9 squared minus 1, which is 81 minus 1, which is 80. Okay. In example D, they're asking me to plug in an f of x. That's what I'm plugging in to the function named g. Okay. So go to the function g, which is x squared minus 1, and instead of the x, I'm going to replace it with f of x. Okay, now since we know what f of x is, it's 2x plus 3. I can replace that as well, and then simplify. So notice that this time you have to FOIL this bracket, 2x plus 3 times 2x plus 3, 4x squared plus 6x plus 6x plus 9. Write it all out if it helps, and then group your like terms. Okay, so I get 4x squared plus 12x plus 8. So that's the function g of f of x. In example E, again, you've got the specific value, f of 1. Oh, I'm missing a bracket here. So find f of 1 first. So go to the function named f, plug in a 1. I get 5. And then do it again. Go back to f, and you're going to plug in f of 1, which we found as 5. So f of 1 is the same thing as f of 5, which is 2 times 5 plus 3, which is 13. Okay, and then the last one, f of x. So this is really asking you to plug f into itself, which sounds kind of weird, right? Don't think about it too hard. Just ask yourself, what are they asking me to plug in? Okay, I'm going to go to f, and I'm going to plug in an f of x. So replace the x with f of x. That's all. Just plugging it in. And then you know what f of x is. It's 2x plus 3. And then simplify it. So this is going to be 4x plus 6 plus 3, which is 4x plus 9. Okay, so those are fairly straightforward examples. Just follow the notation. What are they asking you to plug in? All right, there's a note at the bottom here. It says f of g of x is not equal to g of f of x. And you can look at the example we just did, scroll back up. Example part B was f of g of x, which we got 2x squared plus 1. And g of f of x, we got something totally different. So these things are not equal, clearly. So basically all that means for me is that the order is important. Okay? Order matters for composition. Right? We know that for multiplication and addition, the order doesn't matter, but composition it does. What are you plugging into what? Right? There is an exception of the rule. If f of x and g of x are inverses of each other, then you will have f of g of x will equal g of f of x, and they will both equal x. So if you do the composition of one and you do the composition of the other, they will be equal to each other and they will both equal x. Okay? Now you don't have to memorize that, but I might ask you to check if things are inverses of each other or not. And to do that, you could find their compositions. Or I might say, are the compositions equal? And then you can just plug them in and see whether or not they are. Okay? So you don't need to memorize that. So flip your page here, example 2. A little more complicated. We've got f of x is square root function this time, x minus 1. G of x is x squared. So in part A, we're determining the composition. Notice that this time I used the different notation with the little circle, f of g of x. It does not say fog x. It says f of g of x. I would rewrite that. It's a lot more comfortable looking when we've got the composition written the way we were doing on the other page. Okay, so what this is telling me to do, go to the function f and plug in g of x. Okay, so the function f is the square root of x minus 1. I'm going to replace the x with the g of x. Okay, and then g of x I know is x squared. So I end up with the function square root x squared minus 1. We'll do the same thing for g of f of x. If you want to pause and try it on your own, go ahead. Okay, I would start by rewriting this as g of f of x. And that's telling me to go to the function g and plug in an f of x. So the function g is x squared. So I'm going to replace the x with an f of x squared. f of x is actually square root x minus 1, and when I square it, I end up with just x minus 1. So that's the whole function there for g of f of x. So that's done. Notice that they're not equal to each other. The compositions are different, which just means that they are not inverses of each other, which we could check and find the inverses and so on, but we don't have to here. Okay, in part B, we're going to find the domain of each and every one, f of x, g of x, f of g of x, and g of f of x. Okay, so starting with f of x, square root function, and we know that square root functions have to have positive or 0 inside of them. So square root x minus 1 is what I'm looking at. So has to have x minus 1 greater than or equal to 0, which means x is bigger than or equal to 1. So that's the domain for f of x. G of x, which is a quadratic function, x squared. If you graph it, you see a parabola, all real numbers. No problems there. Okay, so that was fairly straightforward. Now doing the compositions is a little trickier. First of all, let's do f of g of x. So for this function, we got square root x squared minus 1. Now ask yourself where any problems might come from that. And since it's a square root function, I know that the contents, x squared minus 1, have got to be bigger than or equal to 0. Now we have to solve this. Now this is a little more complicated than it looks. If I add the 1 to the other side, I get x squared bigger than or equal to 1. And if you square root both sides here, what happens is that you have to flip the inequality for one of the answers. I don't like doing that. I like looking at this thing graphically. You did it in Math 11 a while ago, I know. Okay, but if you look at the x squared, we know it's just our base parabola. And if you look at the 1, it's just a horizontal line at x, or at y equals 1. Okay, and the question is, when is the parabola, the x squared, when is it bigger than or equal to the line? 1. Right, so the visual really helps, I think. You see it's bigger here, and it's bigger here. And those values would both be when x is bigger than or equal to 1, and on the bottom side there, less than or equal to negative 1. So you can see if you tried to square root both sides here, square root this, you would have got bigger than or equal to 1 and minus 1. And that would be wrong, because you have to flip the sign for the second one. Okay? Alright, so we've got our restrictions for f of g of x. Now there's a catch. Don't you hate that? The catch is this. You have to include initial restrictions. And what I mean by that is the restrictions from the original functions, f of x and g of x. So looking back at the domains we came up for f of x and g of x, bigger than or equal to 1, and all real numbers, anything that we're going to state for f of g of x has to include both of those. In other words, it can't contradict either of those. Okay? So for our restriction, bigger than or equal to 1, that one's fine, because both of the initial restrictions are okay there when x is bigger than or equal to 1. But less than or equal to negative 1 is not fine. And the reason for that is because the function f of x had to be 1 or bigger. Okay? So the only domain for our composed function is the bigger than or equal to 1 part. Alright, same thing for g of f of x. Last one here. Our composed function was x minus 1 from right above here, which has no problems. It's a line, so the domain would be all real numbers. Okay, but the same thing carries through. I need to include the initial restrictions, if there are any, and whatever they are. So looking at f of x, I said that x had to be bigger than or equal to 1, which is contradicted right now. So my actual restriction would be this, bigger than or equal to 1. G of x was all real numbers, so that one will be fine. Okay, so to do restrictions for these composed functions, you have to look at the initial functions, f of x, g of x, and the composed version, and then pick whichever part of that includes the other ones. Okay. Alright, last one here, example 3. So this one is working backwards. We did this in 10.1 and 10.2. So in this case, I'm telling you that h of x is equal to f of g of x, I'm going to tell you what h of x is, and our job is to come up with some possible values, or functions rather, for f of x and g of x. So notice here that this time I plugged in the g of x to the f of x. Alright, so looking at A, I've got h of x is x minus 2 squared plus x minus 2 plus 1. So your job is to look for something that looks as though it was plugged in. So it might be something that occurs several times, but something that looks like it's in common. So the thing that jumps out at me here is the x minus 2. It's in common, it happens twice, it looks like it was plugged into something else. So I might pick that for my g of x, the thing that got plugged in. Okay, so that means I could rewrite h of x instead as g of x squared plus g of x plus 1. So working backwards, right? Now our job is to see, well, what would f of x be then that I plugged the g of x into? And the f of x basically is the other stuff. So it would be an x squared when I replace that with the g of x, plus an x when I replace that with the g of x, and then plus a 1. And you can check it, right? So this is our answer. We've got g of x is x minus 2 and f of x is x squared plus x plus 1. You can check it by doing the composition. Take the g of x and plug it in to the f of x and see if you get where you're supposed to. This one would work. Okay? For example, B, there's a couple ways you could approach this. You could make g of x, the plugged in part, all of the stuff under the square root, so x cubed plus 1. You could make g of x just x cubed if you want. Both ways would work fine. Okay, those are probably the simplest ways to do this. So for me, I'm going to make g of x all that stuff under the square root, the stuff that looks like it went into something else. Okay, which means I could rewrite h of x instead as square root just g of x. Okay, and then f of x has to be the rest, which is just the square root function. That's all that's left. So there we have a possible solution, g of x and f of x. Okay, so make sure you try some of the homework for Thursday. Thursday is our review day, and bring lots of questions and study hard. Okay guys, thanks.